So yesterday we looked at approximating area using a fixed number of rectangles and adding up the areas of the individual rectangles. Today what we're going to do is we're going to first start off by doing that same process with a large number of n where we know the value, and then we're going to learn how to approximate the area for any arbitrarily large n. And then when we're done, we're going to learn how to take n to infinity and actually get the exact area under the curve. So just like last night, we're still going to set up the width of our intervals using b minus a over n. And then in order to do this, because we're going to do a slightly different notation, we want to write down what the sub-intervals are, just to get an idea of the pattern. And then we're going to use the formula to find the heights of our rectangles, and we're still calculating the area using the heights times the width, but now we're going to use sigma notation. So what c sub k actually means in this formula is the value on the x-axis of the right endpoints. So technically we could use left, right, or midpoints to calculate these areas, but the calculations are a lot easier if we use right endpoints, and once we take the limit, we're going to get the same area either way. So we usually use right because it's a little bit easier to standardize and get the hang of. So S sub n means the sum of n rectangles, and so that's going to generate the area under the graph. S sub n is going to be an estimate of the area, but once we take the limit as n goes to infinity, and we've now got infinitely many rectangles, we actually get the exact area under the graph. So here's what I was mentioning about you're going to get the same value whether you use left, right, or midpoint once you take the limit. So we're going to do right endpoints for most of this exercise.